Hello everybody. Today we are going to talk about nth roots, radicals, and rational exponents. And we are going to have two main learning goals today. The first of which is going to be to relate nth roots to rational exponents. And the second thing we're going to learn about is using rational exponents to actually solve problems. So if we're trying to do number one here, we're trying to relate nth roots to rational exponents. Well, first we would need to know what is an nth root and what is a rational exponent. And then we can kind of figure out how those two things relate to each other. All right, so to understand what an nth root is, let's kind of take a step back. So when we think about multiplication and division, we kind of use division to undo multiplication, and we use multiplication to undo division, right? So if we look at this problem here, we have 3x equals 12, right? So we know that we would divide both sides by 3, so in this case we're using division to undo multiplication, and we would get x equals 4. Now, the reason why we can undo it is because it's what's known as an inverse operation. And what we're going to be doing today, while it's not technically an inverse operation, it works in almost the exact same way. We're going to try to undo the other thing. So let's ask ourselves, how would we undo an exponent? Well, let's look at a simple problem. We have x squared equals 16. So what we would do is we know that x squared equals 16 is basically asking what times itself equals 16. So what we would do is we would take the square root of both sides, and of course the square root of x squared is just x, and the square root of 16 is plus or minus 4. Now remember that we have to, when we take the square root of both sides of an equation, if the root is even, in which case all square roots are even, right? Because that's why I put these little 2's here, is to show you that we're actually taking the second degree root, right? So when we take an even degree root, we have to take plus or minus both sides, right? Which is something we did when we did quadratics in Unit 2, but this is just kind of a note just to make sure. So if we start taking the fourth root or the sixth root of things, which are things we're going to actually start to do today, then you'll have to make sure that you take plus or minus both sides because those are even roots and they include positive and negative answers. So just to kind of touch on that a little bit, what happens if we have x to the third equals 64? Now, just like before, when we had x squared equals 16, essentially what we're doing is we're asking ourselves what times itself equals 64, okay? So if we look at this problem here, and we kind of do what we did before, here we have x squared equals 16, right? And we took the square root of both sides. Well, here we have x cubed equals 64. So what we're going to do is we're actually going to take our x cubed and we're going to take the cube root of both sides. Because in order to get rid of an x cubed, we take the cube root and that'll kind of undo the exponent, right? So just like multiplication and division cancel each other out, roots and exponents kind of cancel each other out. So over here, we're going to get equals, we had 64, so this will be the cube root, because we have to do it to both sides, the cube root of 64. And the more of these problems you do, the more you'll memorize some of these numbers. 64 is just 4 times 4, which is 16. 16 times 4 is 64. So 4 times 4 times 4 is 64. So the answer is just going to be x equals 4. And like I said, 4 times 4 times 4 is 64. All we're doing is the main step here is that we're using this cube root. The cube root of x cubed is just x. And then the cube root of 64 is 4. So all we're doing is we're taking the cube root of both sides, and that's how we're simplifying. And that's kind of the idea of what the nth root is. The nth root basically just states that we can take any value of root to cancel out an exponent of equal value. So in other words, if we have x cubed, we can take the cube root. If we had x to the sixth, we could take the sixth root, right? And that would actually cancel out. So in other words, if we have x to the n equals c, this is actually going to turn into, because we can take the nth root of both sides, right? So if I have x to the n, right, I can take the nth root of both sides, and then x to the n, it said equals c. So I can take the nth root of c, right? And then when we cancel out the nth root and then x to the n, that's just going to leave us with x, right? And then on this side, we have the nth root of c. right? So this is a general rule. If you understand this rule here, if you understand that x to the n equals c will turn into x equals the nth root of c, then you're good. You understand everything that you need to understand from the first part. You understand what an nth root is in concept well enough so that we can start comparing these things. All right, so cool. So there's nth roots. So now in order to compare nth roots and rational exponents, well, we know what nth roots are now. So now we have to talk about rational exponents. So what is a rational exponent? A rational exponent represents an exponent and a root simultaneously. This is another way of rewriting the stuff we've been doing this whole time, right? So in other words, we just talked about how the cube root of 64 equals 4, right? So what we can do is we can rewrite this, right? We can rewrite the cube root of 64 equals 4 as 64 to the 1/3 power, right, equals 4. So you notice how, in this case, it's the cube root. You notice that the 3 is on the bottom. It's on the denominator of our fraction here. And everything else is pretty much the same, right? And you'll notice that it's called a rational exponent because our exponent is a fraction. And that's what fraction almost always, rational and the word fraction are always going to kind of connect to each other here. So, all right. So let's break down what this means. So 64 is just our base, right? This is the number that we used in this case. And in the rational part of our exponent, you'll notice that the top is just the actual exponent. This is the same thing as 64 to the first power, right? In the inside here, inside the radical, we have 64 to the first power, right? So this is actually 64 to the first over 3 because the 3 is the root that we divided by, all right? This might be easier just to try a couple and then you'll kind of see what we're talking about. But essentially the root goes on the denominator, the actual exponent goes on the numerator. So let's try some of these. So we have 25 to the 1/2. So I'm going to rewrite and simplify. First, let's rewrite it, okay? Well, 25 to the first is what's going to be inside our radical, right? 25 to the first is just 25. We really don't have to write that. And then we're actually taking the square root. Now remember, if it doesn't have a 2, it's always implied, but I'm going to write the 2 just for the sake of letting us understand what's going on. So this is basically saying the square root of 25. So the answer is simply 5, right? And this one, I overcomplicated it just for the sake of you understanding what this is showing you. This is the same thing. This here is the same thing as saying this, right? I just put the 1 and the 2 here just so you can see where they're coming from. Because when we get into a problem like this one over here, we're going to have to do those in order to make more sense of it, all right? So let's rewrite this. So remember, the 2 up top is the actual exponent. So this is going to be the same as 32 squared, right? But to the 5th root. Okay, so there's a couple ways we can do this. You can actually simplify them in any order you'd like. You can either take the 5th root of 32 and then cube it, or you can square it, I should say, or you can square 32 and then take the 5th root. It's not ultimately going to matter. It's usually easier, just like when you're simplifying a fraction, to make the number smaller first, right? In this case, 32 to the 5th power is just 2 times 2 times 2 times 2 times 2. 2 to the 5th is 32, right? So if we take the opposite, we can see that this is actually 2, right? So in other words, here, let me rewrite this so it makes a little bit more sense, right? So what I'm saying is that the 5th root, this is the way I'm doing the problem. The 5th root of 32, and then I'm going to take that and square it, right? And I'm just bringing the square outside because you can do because they're the same operation, you can do them in any order. So the 5th root of 32, the inside of this just becomes 2, right? And then 2 squared is just 4. So 4 is our final answer for this problem because we did the 5th root of 32 first, and then we squared that answer. And that's really what this is saying, right? This is saying 32. We're going to have to take the 5th root, and we're going to have to square it. You can do those in any order you want. In fact, if you do them in the opposite order, you'll get the exact same answer. All right, so that is a rational exponent. So now we have to compare nth roots and rational exponents. So if we have a value c, and we're taking the nth root of c, that's the same thing as c to the 1 over n. And it's the same way, it's the same both ways, right? So in other words, if I have c to the 1 over n, that's the same as the nth root of c. And this is really the key component from the first part that we learned, right? We learned what is an nth root? Well, an nth root is going to look something like this, right? We have n to the c. And then we said, what is a rational exponent? Well, we turned this into an exponent with a denominator. And now we know how those two things compare to each other. And that's kind of the entire idea behind that first part. So now we're going to take this, we're going to step it up a notch, we're going to get a little bit more complicated. Not honestly, if you could do the 32 and 2/5, 32 to the 2/5, you're doing really well. So, all right. So now let's try to solve some problems, okay? Because our second learning goal is use rational exponents to solve problems. So let's do it. All right. Use nth roots to solve equations. Now this is just going to take some practice because we actually know all the rules we need. We just need to just kind of practice it a little bit. Now, what I would recommend is when you have a problem like this, turn it into a rational expression and go from there, right? So this is the 5th root of 32 and the 5th root of m to the 15, right? So if I rewrite this, I'm going to rewrite this as 32 to the 1/5, right, times m to the 1/5, right? Oh, not to the 1/5, sorry. What's the exponent on the m? It's 15, right? So this will be 32 to the 1/5 m to the 15 fifths, right? Because the m is already to the 15th. So now when we simplify this, right, 32 to the 1/5, we just did that one in the problem a couple times ago. This is just 2, right? This is the same thing as the 5th root of 32, which is the same thing as saying what times itself 5 times, right? So 2, and then m to the 15 over 5, well, this is just m to the 3, right? 15 over 5 is the same thing as 3. So this is 2m to the 3. And if you think about it, if you remember your rules of exponents, anytime we are doing an exponent to an exponent rule, right? If, in other words, we multiply the exponents, we would just multiply them. And it works the same way for dividing them, right? If we have 15 over 5, this is the same thing as m to the 1/5 to the 15th power, right? So you can kind of just combine them, and then you just simplify. So this becomes this, right? And if we look back here, this is essentially, we're taking the 5th root of 32, and we're taking the 5th root of m to the 15, which is what we got here, and what we got here. And then, like I said, some of these numerical ones, like 32 to the 1/5, you got to practice them more. You can throw that into your calculator. Your calculator will be able to figure that out as well. But that's usually just something you're just gonna have to practice, and you'll get more of those down. You'll kind of memorize them as you go. All right, so let's try this one. So we have the 4th root of x to the 20th, y to the 8th. So just kind of try this one real quick. Remember what we did before, where we turned them into rational expressions, and then once you turn them into rational expressions, see where you can reduce it or where you can divide. Same idea. And then just simplify. Okay, so go and pause the video, try that one on your own, and I'll do it here with you in a second. All right, so let's go ahead and do it. So here we have the 4th root of x to the 20th and the 4th root of y to the 8th. So we're going to rewrite these in rational form. So this is x to the 20 over 4 times y to the 8 over 4. Now, x to the 20 over 4 is the same as x to the 5th. And y to the 8 over 4 is the same as y squared. So this is our final answer. Essentially, you're kind of just taking this 4 and dividing it by both numbers, right? If you want to look at it like that. It's better if you understand this form down here, where you got x to the 20th over 4 and y to the 8th over 4, right? Like if you understand this form here, that'll actually help you in the long run more. But just for the sake of it, it's a good start. All right, so now let's look at it if we are actually solving equations. Before we were just kind of simplifying expressions, right? Now we're going to be actually solving equations. So now we need to have x equals something, right? It's kind of the idea. All right, so let's solve this first one. 2x to the 5th equals 64. Okay, well, first of all, we need to get this x to the 5th by itself, just like in any other algebra problem. So if I have 2x to the fifth and I need to get x by itself, I'm going to divide both sides by 2. So let's just go and do that. I'm going to divide this side by 2, divide this side by 2, and I'm going to get x to the fifth equals 64 divided by 2 is 32. And we've seen this one quite a bit now, so hopefully you are understanding the fifth root concept, right? So here, we're just going to do this again. We're going to take the fifth root of both sides. So this is going to give us x equals the fifth root of 32. In other words, what times itself 5 times equals 32, right? And that's just 2. Or what times itself 5 times is 32, which is just 2 times 2 times 2 times 2 times 2, which means that x equals 2. And remember, even though we took the fifth root of both sides, we don't have to do plus or minus because it's an odd exponent. If that was an even exponent, hint, hint, on your try it down here, if you have an even exponent, remember you have to take the positive and negative of both sides. And if you want to plug these into Desmos to see where they intersect, you can always do that as well, right, if you want to check your answer. But I would strongly recommend getting good at this math here. All right, so the next one is for you to try. Go ahead and give it a shot, and we'll come back together here in a second and see how you did. All right, so let's go and give this a shot. It's going to be just like before. We have to isolate our variable first, right? So we have 3x to the fourth equals 1875. We're going to have to divide both sides by 3. I do not know 1875 divided by 3 off the top of my head. I guess it would be, it's 625, right? That's not actually too hard. All right, so let's simplify here. And we're going to get x to the fourth equals 625. Now, because I'm a math nerd and I didn't have calculators when I was younger, I learned a lot of really cool things. I learned that 25 times 25 is 625, which means that 5 times 5 times 5 times 5 is 625, which means the fourth root of 625, which is what we're about to take, is 5. So if I take the fourth root of both sides, right, I'll get x equals the fourth root of 625. And then I just told you that the fourth root of 625 is 5. But, as I stated before, that's not the answer, right? Because when we take the fourth root of both sides, because the fourth root is an even root, we have to take the positive and negative of both. So x actually equals positive and negative 5. And that's our answer. So you'll notice we have 2 answers here, which means we have 2 imaginary answers. Hopefully you're remembering that from our last unit when it came to polynomials. We should have 4 answers, right? Because this is x to the fourth. At least, we know that we have at least 2 real answers, right? Okay. All right, so that kind of solves all of our nth root equations. So let's go ahead and look at our learning goal, right? So we said that by the end of this, we wanted to be able to use rational exponents, in other words, exponents that are fractions, to solve problems. So if we start off with an exponent, we have c to the m over n, where m and n are both numbers, and obviously n can't be, well, n can be 0 in very rare situations, but let's not worry about that. So if we have c to the m over n, what that's going to equal is c to the 1 over n times m, right? In other words, it's c, we can either take it as a root first and then an exponent, or we can take it as an exponent and then a root. You can do it in either order. In this case, we did it as a root times the exponent, right? And that's going to equal the nth root of c times m, right? So if we do this, it's actually taking the square, or the nth root of c, and then multiplying it by whatever exponent m is. So the nth root times exponent m. And that's all we did up here, right? This is just, so you should be able to, if you can do a bunch of problems and you can do the steps, you should be able to explain the steps in a more generalized way, which is what these kind of formulas are. And remember, if you start at this end over here and work your way over here, you can always go this way and work your way back, right? That's how equations work. You can go from one way to the other. So if you start with a radical form here, you can turn it into an exponential form. And if you have an exponential form, you can turn it into a radical form. All right, now the kicker. This is the fun stuff here. We have an application problem. So let's do it. So a garden water fountain is made of 2 cubes. The larger container has an edge length that is 2 centimeters longer than the edge length of the smaller cube. Okay. when the larger cube empties into the smaller one, how much water will spill over the edge of the smaller cube into the base if the volume of the larger cube is 729 cubic centimeters? All right. So basically what this is saying is we have this big cube here, and it has a bunch of water in it, and it'll eventually tip over. Once it gets full, it tips over because it says empties, right? So we're assuming that it's full of water. As it empties, it'll empty into this smaller cube down here that's connected to the base, and then because this cube's bigger than this one, it's gonna have extra water, right? So that extra water falls down into the base, and we're trying to figure out how much water is going to actually end up being in the base once this bigger cube falls. So if you think about this, if our big cube is full and then it empties into this smaller cube, and then whatever's left over is going into the base, you're just going to subtract, right? So it's, in other words, it's going to be bigger cube minus smaller cube is going to be whatever's left over in the base. So let's just kind of write that down as we'll say like the volume of the large cube minus the volume of the small cube is going to equal the volume of the base. Makes sense, right? Okay, now we have to figure out what that means, because we should be able to figure out the volume of the large cube and the volume of the small cube, considering they already told us the volume of the large cube is 729 cubic centimeters, right? So the volume of the large cube is 729 cubic centimeters, right? Okay. All right, last piece of information they give us is that the large container has an edge length 2 centimeters longer than the edge length of the smaller cube. Okay, so if we start to look at this, right, what we know is that if let's say that if these side lengths are x, let's take our smaller cube. Let's say these are all side length x, right? We know that the bigger one, all of the sides are 2 centimeters longer, right? Now it's a cube, so all 3 dimensions are the same, right? The volume of a cube is very straightforward. It's just length times width times height, but all of those might as well just be the same. Might as well just be x to the third, right? That's why we call it cubic whatever, right? So if that's x, then this is going to be, well, 2 larger than x is just x plus 2. So all of the side lengths of this are x plus 2, right? In other words, our large cube, the volume of our large thing, is x plus 2 cubed, right? And we know that that whole thing equals 729, right? And then we know for our small one, so the volume of our small is just x cubed, right? And we don't really know what that one is yet. So let's go ahead and just solve for the first one. Because if we solve for x in the first one, we can plug x into the second one, right? Okay, so we have x plus 2 to the third. Okay, let's just rewrite this down here. So we have x plus 2 quantity cubed equals 729. Okay. So what are we going to do? We're going to take the cube root of both sides, right? We take the cube root of this side, and we take the cube root of that side. All right. So 729 is, well, 9 times 9 is 81. 81 times 9, 729. So we know that this is 9, right? So we know that x plus 2, because we eliminated this and this, like, cancel, right? So all we're left is the x plus 2 equals, well, the cube root of 729 is 9 times 9 times 9. So x plus 2 equals 9. And hopefully I don't have to help you from here. We subtract 2 from both sides, minus 2, and x equals 7. All right, awesome. Now, remember what we're trying to find is how much water is in the base, right? So if we know that the volume of the first one is 729, we need to find the volume of the smaller one so that we can compare them, right? We can subtract the one from the other. So we also know that the base is just going to be x cubed, or the cube connected to the base is x cubed, right? So x cubed, well, x is what, 7? So if x cubed is 7, then we can look at this as 7 cubed, right? 7 times 7 is 49. 49 times 7, I don't know that one off the top of my head. 49 times 7, 343. Easy enough. So this one is 343. And now remember our original formula down here is 343 cubic centimeters, right? And that's going to equal the base volume. Okay, so now we just subtract 729, 343. 729 minus 343, 386. So, yeah, it looks like the bigger cube is over twice as large. In other words, the volume of the base equals, oh, it went way too fast. 386. 386. All right. Fun stuff. So, just a quick recap. First of all, we talked about what is an nth root, right? And we discussed that an nth root is basically you can take roots beyond the second degree, right? It's not only square roots. We can take cube roots. We can take fourth roots. And those can be represented, if we have x to the n equals c, we can rewrite that as x equals the nth root of c. And that's why we call them nth roots. All right, and then we talked about what is a rational exponent. Well, rational just means fraction. Exponent, you know what an exponent is. So we have exponents with fractions. And the bottom part of the fraction is the root. The top part of the fraction is the actual exponent. It's what the base is being raised to, right? That power. And then we tried a couple problems. And we decided that if we have the nth root of c, that equals c to the 1 over n. In other words, the denominator is the same as the root. All right, then what we did is we started solving problems where we actually, it kind of looks like we just divided it out, right? But we took, in this case, we took 32, we took the fifth root of 32 and the fifth root of m to the 15, and we simplified that out. And we came to the conclusion that we can use this formula. If we have c to the m over n, right? Remember the n is the root, the m is the exponent. So we can say that that equals c to the 1 over n, right? In other words, we're taking the nth root of c and we're multiplying it by m, which is the power, right? The actual exponent. And this is what this would end up turning into, right? We'd have the nth root of c times whatever the exponent was, in this case m. Okay? And then we had a really cool problem. That drawing is even really cool. You guys got to give me props for that drawing. But yeah, we did this really cool problem where the big cube unloads into the small cube here. And we used a little bit of logic and understanding of basic shapes and kind of went from there. All right. Well, if you have any questions, let me know, and I'll see you in the next video.